right, let's go over this one. 1.9, describing location and distribution. What's our learning target? After this lesson, you should be able to find and interpret a percentile. So the percentile is a big idea here. In a distribution of quantitative data, I did something new here. You can locate these lessons. So the idea of percentile is found in lessons in the 2 examples below, and then also in questions 1 and 4 in your homework. Estimate percentiles and individual values using something called a cumulative frequency graph. So we're going to use the previous concept of frequency, but now add this idea of cumulative, and then find and interpret standardized scores, z-scores, in a distribution of quantitative data, and you can find those in the lessons and homeworks below. All right, go ahead and pause the video so you can copy that down, and then I'll just talk through them. So statistics, we've been talking about describing data numerically, so with numbers, okay? We've talked about this in orange, which is the center. We've talked about, right, this idea of center. Center is measured with the mean, the median, and the mode. Remember, the mode's not a great one. And then we've talked about spread, right? So the range, that would be finding the max and the minimum. The IQR, we talked about that one. That is the box in the box plot, right? The IQR is Q1 minus Q3, and there's the median there, so but it's the whole box, right? Variance and standard deviation are measures of spread, and we've talked about how really it's kind of like how far away from the average is it going, the center. And the new one is location. Quartiles, which are 25% chunks, like think of quarters in a dollar, to percentiles and z-scores. So we've talked about percentiles quartiles is the last lesson. Percentiles is a little bit from last lesson, but mostly today, and standard z-scores. What is a percentile? Percentile describes the percentage of data that is below the particular data point, like a quartile. What's the formula here? Percentile equals the number of scores below, I'm going to emphasize that again, below, over the total number of scores times 100. So number of scores below X, whatever they give you, divided by the number of scores, you'll get a percent, and you multiply by 100, you get a percent, and you can change that to something called percentile. All right, what are some misconceptions? On a test, a student's percentile is a student's percentile the same as a percent correct? So the question is 80 percentile the same thing as 80% correct? The answer is no. If you receive a 80% on a test in a class where 10 people score better, you're in the 67th percentile. So how did I get the answer of 67 percentile? Okay, so again, let's just say you are here, you're the stick figure, and we said in there that 10 people scored above you, so this is the 10. And let's just say you're in a class of 31 people, so that means there's 20 other people in the class. Okay. That means that 20 people below you, so 20 people below, I'm just using the formula from over here, number of people who scored below, over the total, well, I guess you would need, that would be wrong. A total of 31, and you'll get something close to 67. And that would be like the 67th percentile, 0.67, somewhere around there, and then multiply by 100, you'll get close to 67th percentile. Okay? All right, baseball. The data below shows the number of wins for each of the 30 major league teams in 2009. Calculate and interpret the percentiles for the Colorado Rockies, New York Yankees, and the Cleveland Indians. Okay? All right, so The Colorado Rockies had 92 wins. So let's go ahead and find them over here on this stem and leaf plot. Quick review of the stem and leaf plot. It tells you with a key that the number on the left here is a stem. And the number on the right is the leaf. So what does 5 and then the bar 9 mean? Well, that bar separates the stem and leaf right here. The stems there in blue are actually multiplied by 10. So 9 times 10 gives me 90, and 10 times 10 gives me 100. So this number right here represents 103. Okay? Now, the Colorado Rockies are at 92. So let me erase a bunch of this. Okay, so let's just erase it all. Might be faster. Okay, 92. So this is where the Colorado Rockies are, 92. Okay, now let's count how many numbers are above them. Okay, 1, 2, 3, 4, 5. Okay, there are 5 numbers above them with more wins. Okay, the 1 here represents the Colorado Rockies, and then if you count below, if you count all of these numbers here in blue, right, 59, 62, 64, if you count all of those numbers, that's 24 teams. So this is how I think of it. Here's the Colorado Rockies. There's 5 teams above them. That means there's 25 teams below them, which equals the 30 teams in the Major League Baseball, which means there are 24 teams below them. So 24 teams below them divided by 30, the total, that's the formula, right? Then you get basically a decimal, 0.80, and you multiply it by 100, you get 80% or 80 percentile. What does that mean? The Rockies are at the 80th percentile because 24 out of the 30 teams did worse or below them. Okay, let's try the New York Yankees. The New York Yankees had 108 wins. Okay, let's locate 108 wins. Let's erase all this. Okay, so 103 wins is right there. Okay, you can turn your head sideways. Now, that basically means that all of this data here is below them, right? The Yankees had the most wins that year. Okay, so what does that mean? So if the Yankees are, again, this is my visual, they are the only one, right? They're at the most. They had the most wins that year. That means there are 29 teams below them. Well, 1 plus 29 gives you the 30 teams in the Major League Baseball. So, if you, so 29 teams below divided by the total, Yankees are at the 97th percentile. How did I get that? 29 divided by 30 and then multiply by 100. They're in the 97th percentile because 29 out of 30 teams did worse than they did. Okay, go ahead and pause and see if you can do the Cleveland Indians. The Cleveland Indians had 65 wins. 65 wins. So let's go ahead and find them. Let me erase all this. 65 wins are, okay, so they're both. You're not sure which team it is, so it doesn't matter because they're both at the same percentile. Okay, so here they are. 1, 2, 3. There are 3 teams below them. So the Cleveland Indians had 65 wins. So this team had 64, 62, 59. Okay, so that means there are 3 teams below them. Okay, the green here represents the Cleveland Indians. And that means there are 26 other teams that are above them who had more wins than they did. A number bigger than 65. So what is the number below? That's only 3 teams. divided by the total. And if you reduce that, you get 1/10, which is 0.10. And if you multiply by 100, you get 10%. The Indians are at the 10th percentile because 3 out of 30 teams did worse than they did. Let's go on to the next page. All right, let's go to the next page, example number 2. Why don't you read that to yourself, see if you guys can answer those questions, and then I'll go over it with you and just press play when you're finished. A talent show was held for the 15 finalists. I was like circling. There are a total of 15 here. In the teen idol contest, each performer received a score from 0 to 30, with 30 being the highest. Arrange the list in ascending order. And we're doing that because I need to figure out stuff, right? So let's put these in order. So I see 4, 6. Missed one. 5. Pencil, guys, pencil. 5, 6. Then a 9. Then 11. Did it again. 10. 12, 13, 14, 15. 17. 18. 19, 20, 21, 22. 22, 23, 24, 25, 26, 27, and then 28, 29. Okay, and then I like to just go back and actually number these to make sure that there are 15, right? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Perfect. Okay, then what's our formula for percentile? Just look above. If you guys haven't been practicing in math, you should always write down the formula. Number below over the total times 100. Okay, so let's figure out where Victor's at. Victor is 28th. Okay, so again, you like my visual? I don't know. This helps me. This is Victor, and Victor is one person. There is one person above Victor in green, and we know that there's a total of 15. So the question is, how many are below Victor? What color can I use? Orange, yellow. It doesn't really come out really well in this. Okay, so that means all of these people are below Victor. Okay, so that's going to be 13 people. These 13 are below Victor, right? So what is Victor's, how many people are below Victor? That we said was 13. And over the total times 100, you'll get, so Victor has a score of 28. That means Victor scored at the 87th percentile in the contest. Again, real life examples, you guys get your PSAT scores. Just look at where your percentiles or your SATs. All right, let's go over this one, which talks about cumulative relative frequency. An ogive is a graph that represents cumulative frequencies or cumulative relative frequencies of a data set. Remember, that just basically means add up. And then the word frequencies is just a percent. You're adding up the percents of a data set. It is pronounced ogive. That's the fancy word. If you just use, you can use relative frequencies, or you can use ogive. It is constructed from a cumulative frequency histogram or a cumulative relative frequency histogram. For our purposes, we will create just the cumulative relative frequency ogive, as it enables us to estimate what have we been learning? Percentiles. All right, let's take a look at this example below here. Example number 3 is shampoo data. The shampoo data represents various shampoo bottles and their cost per an ounce measured in cents. So over here, I kind of made this table, and we just need to do a count, right? So, question: how many of these bottles over here in that table are between 0 and 9 cents per an ounce? That's 9 and 9, so we have 2. And we said, if you count up how many bottles there are, 3 times 4, that's 12 bottles. So our relative frequency, so that's 2. I mean, those are just kind of like tally marks. So that would be, our relative frequency would be 2 divided by 12. And if you made that a decimal, you would get 0.1667. Okay, press pause, and then why don't you get the rest of those? All right, 10 to 19. 1, 2, 3, 4. So there are 4 of these. So 4 out of 12 gives me 0.333. 20 to 29. 1, 2, 3. Oh, I was going to change colors. 1, 2, 3. 1, 2, 3. 3 out of 12 is 25. Between 30 and 39. So again, you might be asking, how did I figure out those bins there? These are the bins, right? And you're kind of just thinking of your range, your max versus your min, and then how can you break them up? We talked about before in histograms, kind of like how many bins do you create? And it's kind of up to you, but you don't want too many and you don't want too few, so it's kind of ambiguous. 2 out of 12, which is the same decimal as above. So this should be a review. And then 40 to 49. So that's just one of these. So 1 out of 12, and you will get 0.0833. Okay, so again, if you add all those up, you should get 12 out of 12, and that's what? 100%. Okay, this is where it is new, okay? Cumulative just means to add. So in my class, we have cumulative quizzes. What does that mean? So all the information you learn from August, and we're in the middle of September, so whatever you learn in the beginning of August is still going to be on the quizzes. The quizzes keep adding up, right? First, I quiz you on weeks 1 and 2, and then on week 4, I quiz you not just on weeks 3 and 4. I'm going to quiz you on weeks 1, 2, 3, and 4, and then quiz 6. The next quiz, you're going to have it all up to weeks 1 through 6. You add them all up. That's the big idea, okay? So watch. I have this 2, and we already know that it's just 2/12, which is 0.1667. Okay? All right, pay attention. The next one, you're adding 2 plus, look at this one, 4. 2 plus 4 is 6. Okay, so now I get 6/12, which gives me 0.5 or 50%. Okay, what's the orange? Okay, watch. 2 plus 4, and then what's my next color? Orange. Plus 3. You see the 3 here? And that will give you a 9. So 9/12 gives me 75%. Okay, so 2 plus 4 plus 3, and then blue, I have 2. This will give me 11. 11/12 gives me 0.9167. Okay, so then you add all these 2 plus 4 plus 3 plus 2 plus 1 gives you 12. And 12 over, again, you're using that one right there, right? This gives you 100%. Okay? So another way of saying this is just, you're going to your counts, and then the first one, you're just adding the first one. And the second one, you're adding the first 2 bins. And then the third one, you're adding all 3 of these. And then the fourth one, you're adding all 4 of them. And then the fifth one, you're adding all 5 of them. Okay? All right, let's actually graph this. So create a relative frequency or ogive. Can't spell. All right, so let's just do the histograms. Let's do this in a dark color. And we said that these are ounces of shampoo, right? And we did something like this, okay? I'm just doing a regular histogram. And this is based off of the table. And we're doing this is going to be a cumulative frequency. Cumulative frequency. 20, 30, 40, and 50. Okay? So how many bottles were I don't have a count here. 2, 4, 6, 8, 10, 12. 2, 4, 6, 8, 10, and 12. So we had, let me see if I can just by color coding. Okay, we have 2, right? So this is what that looks like. And then we added 2 plus 4, which would give me a 6. And then we did 2 plus 4 plus 3 equals a 9. So this one's going to be 9. And then we did 11. And if you notice, it'll always get to 100% or it always goes positive. I don't know if that makes sense. And then 12. Okay, so this is a cumulative frequency histogram. Okay. So that's what that one looks like. But now if I change it to a, let's change it now. Let's change it. Now I'm going to do some white. We're going to call this a cumulative relative frequency. What's the difference? Remember, this one is percents, and that one in purple is just the counts. But remember, cumulative means just total. So let's try to see if we can hammer this home in big idea. Okay, the purple graph I have below is just this one right there. And the cumulative I'm going to do here in white. Okay. All right. Now I need to change my scales. So let's call that 100%. And let's do something like, I don't know, 0.2, 4, 6, 0.8, okay? All right, what's the difference here? The difference on this one, though, is if you'll notice, you're kind of going at the front of the watch, 0.16, and then we're at 0.5, and then 0.75, 0.96, and then 0.1. So it's kind of looking something like this, okay? Something like that in white would be our cumulative relative frequency. All right, let's go over this one. Household income. Here is a cumulative relative frequency. Remember, the word relative means to add, and relative means the percentage, and frequency means counts. So this is a graph showing the distribution of median household incomes for the state, 50 states, and the District of Columbia. So if I ask you, kind of like in every state, how much are you making? I take all the averages, and that's what the graph looks like. 4A, California with a median household of 57,000 is at what percentile? So basically, what you want to do is 57,000 is money. And if you look at my graph, you have cumulative relative frequency and household income. Income is money. So I'm going to start here at, in between my intervals here, between 55 and 60 is 57.5%. $57,500. So they should have wrote measured in thousands of dollars, right? Because you're taking this number and multiplying it by 1,000, and it gives you 60,000. So $57,445 is around here. And what you're going to do is you're just going to draw a straight line up the best of your ability. And then you're going to go over to the left to the y-axis, and it's going to help you figure out a number over here. Well, that is 0.8. Now, again, that is a decimal, and you change that to a percent, you'll get the 80th percentile. That's why I wrote as the answer. California is at approximately the 80th percentile, which means about 80% of states have a median incomes less than $57,445. What does that mean? We kind of talked about how percentiles is like a rank, right? So if that means 80% of the states have how much money they're making, there's 80 states below, and there are approximately 20 states above California. What does that mean? California, you actually make a lot of money to work in the state. Question 1B, what is the 25th percentile of the distribution? So if you go to 25% on your graph, is that the y-axis or the x-axis? You'll notice here that they're measured in these dots, so halfway between 0.2 is 0.1. So each of these tick marks here are 10%. So it's asking, when is the 25th percentile? 25th is below 30%, so between 0.2 and 0.3 is 0.25. And we're going back to my graph. And once you hit the graph, then you're just going to go below. Okay? And that's somewhere around 45,000. Approximately 45,000. 4C, what is another name for this value? They're asking what is another name for the 25th percentile That is something we learned previously. That's called the first quartile, Q1. So if you think about it, the quartiles we learned in the previous lesson are just in the fixed numbers, 25, median, 50, third quartile, 75%. 4D, make a relative frequency histogram of these data. So see the histogram above that was added to the original that says graph. Don't you like my writing? Graph. Okay, so previously we did make a cumulative relative frequency histogram. So you'll notice that it's at these dots, and that's the bin, right? And then here, and then coming up to about there. Remember, histograms are touching. And so these points for our cumulative relative frequency, or our ogive, is actually in the top left corner. Do you see that? And so you just go over here and make all of these graphs. And remember, the top right, they're always going to hit 100%. So you're always going, this graph's always going to be positive going from left to right. Always positive. Where is the graph the steepest? Well, if you look between 40,000 and 55,000, I circled, steepest means the hardest climb. It's kind of like the most exciting part of a roller coaster. And down here, it's kind of flat, right? But here, a lot of things are happening. So what does it mean? If it's a sharp incline, that means there's more data. More things are happening. That means more data. That means more states have their incomes between there. So I said between 40 and 55,000. There is a steep incline here. And then the next question says, what does this indicate about the distribution? There are lots of states with median incomes between 40,000 and 55,000. So if the data climbs really fast, that means there's a lot of states there. All right, next page. Who's taller? You guys are always fighting, right, with your siblings. Macy, a 3-year-old female, is 100 centimeters tall. Brody, her 12-year-old brother, is 158 centimeters tall. Obviously, Brody is taller than Macy. Let's draw a picture. Here is Macy, and she is 100 centimeters. And Brody is 158. So here's Brody. Obviously taller at 158 centimeters. But who's taller, relatively speaking? That is, relative to other kids of the same ages, who is taller, right? According to the Centers of Disease Control and Prevention, the heights of 3-year-old females has a mean of 94.5. Okay, so let's see if I can kind of show you a picture. That means everybody else is 94.5. And a deviation of 4 centimeters. Okay, so the 4 centimeters here just means that some people are a little bit taller than 94, so you add 4, or you can subtract 4, right? Some people are taller, some people are shorter. The mean height for 12-year-olds is 149. So there's the average 12-year-old male with standard deviation of, what do we say, 149. And then you can add plus 8 or minus 8 as an average. Okay, that's what standard deviation means, right? It's the spread. So what does that mean? Brody, if you subtract those, Brody is farther above the average. If you subtract Brody minus the average, 158 minus 149, is 9 centimeters above. Then Macy, you subtract on Macy's 100, she's taller, right, than the average. 100 minus 94.5, that gives you 5.5 centimeters and we call it absolute sense. So we're just subtracting those values, right? But we have more advanced math than just subtraction. We can also most consider, what's the best measure of center here? Standard deviation. All right, so we have this new concept. Let's go to the next part. How do you calculate and interpret a standardized score? Okay, so these are essentially the same. Standardized scores you need to refer to as z-scores. I don't know why it has the letter z, because standardized scores do not start with the letter z, but they call them z-scores. Okay, those are synonymous right there. What's our formula? Let's write down the formula. Star, star, star. Write down this formula, highlight it. A z-score is equal to the data minus the mean over the standard deviation. So again, this is your x bar, and this is actually your data, the x value. Okay? And z, standard deviations, we call it either above or below the mean. All right, do z-scores have units? No. Note, is being 10 above average a big deal? And the answer I'm going to say is for height, let's just say you're 10 inches above average. Then I would say, yeah, that's a big deal. 10 inches could put you in the NBA. I'm almost 6 feet tall, and I was 10 inches tall. If you're 6'10", I can play in the NBA. Well, that's a good height, right? But how about for salary? How about for in dollars? Is $10 more total a year a lot of money? The answer is no. So, what does the sign is like positive or negative, of a standardized test score tell you? A positive z-score, the observation is above, and a negative z-score is below. Let's give you a visual of this. Kind of tie back to that distribution, this graph here. Okay, if this was the center, the mean, or the median are the same, then above would be in this direction, right? That would give us a positive z-scores. And a negative z-scores would be below, down this direction. Okay? So let's figure this out. Let's go back up. Let's go to, so who is truly taller, Macy or Brody? What color do we use for Macy? Macy was pink. Macy, we're going to use that formula, so let's write down the formula again. I like to write down the formula every time. Sounds silly, but at least you know where the information is coming from. X minus the x bar over the standard deviation. Okay, so how tall was Macy? That's the x value here. How tall is Macy? Let's use our highlighter here. Macy is 100 centimeters. So this part here is how tall Macy is. Macy is 100. Can't see that, come on. 100. Minus, what is the average that CDC said? Well, the average we said was for 3-year-old females was 94.90. 94.5. So the average right there is 94.5. Dope. 94.5. And then the standard deviation, it tells you there too, the standard deviation of 4. So that's how I'm getting these values. So if we do our z-score, you'll get 1 point, this is going to be a positive, 1.38. What does that mean? 1.38 standard deviations above the mean. All right, let's do Brody. Write down the formula. Remember, standard deviation is going to be abbreviated with S. Okay, so let's figure out his z-score. So, Brody had a, how tall was Brody? Brody was 158 centimeters. 158 centimeters. Okay, what was the average? The average for 12-year-old males was 149. Let's write that, 149. And then what was the standard deviation for 12-year-old? That would have been 8. So if I calculate all that, you're going to get 1.13. 1.13 standard deviations. Is it plus or minus? Plus. If it's plus, that means it's what? Above or below? It'd be above the mean. All right, what does this mean? Which one has a greater standard deviation? Which one has a higher z-score? Relatively. So now we're comparing apples to apples. Relatively speaking, Macy is taller. Again, you're not thinking of just, well, she's a little bit Brody compared, a 12-year-old compared to a 3-year-old, but Macy compared to 3-year-olds is taller than most 3-year-olds versus Brody, who is taller than most 12-year-olds. So if you compare it, Macy is actually taller. All right, let's go on to the next page here. The single season home run record for Major League Baseball has been set just 3 times since Babe Ruth hit 60 home runs in 1927. Roger Maris hit 61 in 1961. Mark McGwire hit 70 in 1998, and Barry Bonds hit 73 in 2001. In an absolute sense, Barry Bonds had the best performing of these 4 players because he hit the most home runs in a single season. Just look at the numbers, just a straight highest number, the maximum. However, in a relative sense, this is not true. Baseball historians suggest that hitting a home run has been easier in some eras than others. This is due to many factors, including quality of batters, quality of pitchers, the hardness of the baseball, dimensions of the ballparks, possible use of performing-enhancing drugs. To make a fair comparison, we should show how these performances rate relative to other hitters in the same year. So in this, I have the years, I have the baseball player, how many home runs they hit. The mean is the average in which all of those players that year, what were they hitting? And then the spread, how far apart was it? Okay. All right, calculate the z-score for each of the players. Okay. Go ahead and calculate this z-scores for each of those. Again, write down the formula, and then we'll compare them. So for Babe Ruth, again, z-score is equal to the data minus the average over the standard deviations. So if I look at what Babe Ruth hit 60 home runs. And the average was 7.2. And the standard deviation was 9.7. So if you put in your calculator, 60 minus 7.2, and then you divide that by that number. Let me calculate that in my calculator right now. And I get Ruth has a z-score of 5.44. All right, let's try Maris. Again, write down the formula every time. The number minus the mean over the standard deviation. So Maris had 61 home runs. The average was 18.8. Again, this chart right here is like super helpful because I gave you all the numbers. You just have to subtract them. But that won't always be the case. I might give you a list of numbers like number of home runs Roger hit in his lifetime, and you would have to take all of those years and use that data. And the standard deviation is 13.4. And if you 61 minus 18.8 divided by 13.4, you put in your calculator, boom, 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 and that gives you 3.15. So Roger Maris has a z-score of 3.15. All right, let's go with McGuire. Z-score is his number minus the mean over the standard deviation. How many home runs did he hit? He hit 70. And then the average was 13.4. And nope. I looked at it wrong. Let's try that again. 70 minus 20.7 over 12.7. And that gives Mark McGuire a z-score, 3.88. And then Barry Bonds, z equals, again, his number minus the average over the standard deviation. So 73 minus 21.4 over 13.2. Your z-score is going to be 3.91. All right, which one of these has the highest z-scores? Relatively speaking. So when I say relatively, you're kind of comparing apples to apples. The z-score is the easiest way to compare people. Babe Ruth is still the home run king. Why? He had the highest z-score because you're comparing all the players in his era at that time. All right, this one's just working backwards. Example number 7, more baseball. In 2001, Arizona Diamondback Mark Grace. Grace's home run total had a standardized score of z equals negative 0.48. You should think about something. Negative. What does that mean? Is he good, average, or bad? I like Mark Grace. I grew up with him, but unfortunately a negative score is bad. That means he's below average in terms of how many home runs he's hit. Interpret this value and calculate the number of home runs. So, what we just read, what year was that? 2001. Using the table above, answer these variables. So which player was in 2001 in that chart? That was Barry Bonds. So, Barry Bonds. And what was the mean that year? The mean in Barry Bonds of 2001 was 21.4. So now we're kind of comparing a new player, but we're still using all the players' averages in 2001. What was the standard deviation? That was 13.2. Again, I just got those numbers from 2001. Let me just use a highlighter. 2001. I'm using all of that data right there. Okay? All right, so I got the data. We did that one. Whoops, I should have changed those numbers. 6b, Should be 7b. Write down the z-score formula. Z equals the number minus the average over the standard deviation. And we just substitute all these in. All right, what do we have? We have the mean, 21 point. See, 21.4 is the mean. So I'm going to write 21.4 there. And we're trying to find, interpret this value and calculate the number of home runs he actually hit. So the number of home runs are actually going to be the x value, which we don't have. Okay, how about the standard deviation at that time? Standard deviation of that year was 13.2. 13.2. Okay, how about this? What was the z-score? Well, the z-score was 70 negative 0.48. Okay, so what do? We substituted our numbers. Now we're going to solve for x. All right, so you can do a couple of things here. You can cross multiply. Not cross multiply. Yes, cross multiply. We're solving proportions. You just put it over 1 and you can multiply 1 times this. That would just read x minus 21.4. And then over here you have negative 0.48 times 13.2. And then you can just add 21.4. So all of that plus 21.4. And then you'll get x equals a number. And the number I get is approximately 15. What does that mean? Mark Grace hit a home run total. Remember, the negative represents what? Below. And the z-score below league average. Mark Grace hit approximately 15 home runs in 2001. All right, so that summarizes just lesson 1.9, describe location in a distribution. See you guys.